Hello, my name is Eli Van Cleve, and today I would like to discuss with you quantum entanglement. Now, before I get into what quantum entanglement is, I would like to describe what it means for something to be inside of a quantum mechanical state. Let's take the electron as a good example of a quantum mechanical object. Now, an electron has a spin to it, believe it or not, just like the Earth. The Earth spins on its axis such that the sun rises in the east and falls in the west. Now, of course, the Earth could theoretically spin the other direction, like other planets in our solar system, and particularly Venus. So the Earth can spin one direction or the other, and so can an electron.
What that means is, if I have an electron and it's in free space, just out there, it's not bound to an atom or anything like that. This is the simplest possible example. The electron will have a spin to it, but what that means quantum mechanically is that it doesn't have one spin or the other. Let's define its spin this way as being positive 1/2, and spinning the other way or this way as being negative 1/2. In fact, the spin of the electron is in both directions at the same time. It's in what we call a superpositional state of plus 1/2 spin and minus 1/2 spin.
It will actually go into one of those states if I make a measurement of it. Once I make that measurement, I perturb the system. I introduce some kind of electromagnetic field or something like that. Then the spin of the electron will become either plus 1/2 or minus 1/2. So that's a regular quantum mechanical object in free space. It exists in a superposition of this quantum mechanical state. Now, quantum entanglement is if I have another particle, let's say a positron. Now, I'm going to back up for a moment and describe to you what a positron is. A positron is just like an electron. It has the same mass, it has many of the same properties, with the exception of one. And that is that a positron has a positive charge to it. An electron has a negative charge to it. You might be more familiar with charge when it comes down to things like sides of a battery, the positive terminal of the battery and a negative terminal of the battery. You can imagine the electron being the negative terminal of the battery and the positron being like the positive terminal of the battery. Now, this positron is the antimatter version of an electron. And so these guys are identical. You've got matter, the electron, and antimatter, the positron. Now, if you can imagine that these two guys are somehow quantum entangled with each other, what that means is that although in free space, this electron has both positive 1/2 and negative 1/2, and the positron has both positive 1/2 and negative 1/2 spin, and their superpositions. If I measure the spin of the electron, I introduce it into some electromagnetic field, then what happens is I define the spin of the electron when I do that. And I define the spin of the positron when I do that. In fact, now it has a spin. So if I sat down there and I measured the spin of the electron to be positive 1/2, suddenly the positron becomes negative 1/2. It has that spin. That's what quantum entanglement means. Now, you might be first saying to yourself, well, how in the world would I ever find a situation where an electron and a positron are going to be quantum entangled? And the simplest example of that is, in fact, it happens in real life, because if I have a photon, a piece of light that has so much energy to it, it will actually spontaneously go away and create an electron and positron pair. And this actually happens. This happens in decayed nuclear atoms. There's so much excess energy within them. So now that you understand what quantum entanglement is, are there applications for it? And the answer to that is yes. It's very important in quantum computers. What a quantum computer is it doesn't use transistors as the bits, as the formation for what does the calculations. What it uses are quantum mechanical objects, like atoms, like electrons, like light photons. And sometimes you have to entangle those states together in order to make it work. It also may be used in things like quantum cryptography, where in fact what it is I want to send a message to you. Hi, you doing there, guys? But I only want you to receive it. How can I possibly know that no one else intercepted that message? Well, if I quantum entangle a part of that message with some object, like a photon, and I sit out here with this other photon, I can be able to tell when you've received that message and if someone else has intercepted. So it's something which people are very interested in using. And this is how quantum mechanics is really, really important for national security reasons in this country and others. Thank you so much for watching this video. I hope you've learned something today. If you've enjoyed this content, please like and subscribe. Have a wonderful day. Thank you very much. Bye-bye. This has been a video from Van Cleef Scientific. If you like this, please like and subscribe for more content.